Thank you, Monica. Is there a clicker? Thank you. Thank you, Monica. Good afternoon, Warsaw. It's great to be back here. I love the passion. I love the energy in this event. I can tell you it's quite unique. I've been to quite a few events in my life, and this is very, very unique. So I enjoy being here. It's a difficult topic that we're going to talk through, but the timing for this is just about perfect because we're right after lunch, and so most of the lions and lionesses are asleep, right? And so the questions are a little more gentle typically, but nevertheless, I have about 15 minutes of material, and we'll have about 7 or 8 minutes for Q&A at the end. So get your questions ready, and we can have a little debate around this. So when I said this is a difficult problem, what is so difficult about zero-emission aviation? Well, there's a number of elements to it, really. First of all, when you think about emissions, everyone thinks about CO2 immediately because of the global warming potential, right? Justifiably so. But there's also NOx, and NOx still attacks the ozone layer, right? There's also particulate matter, which is soot, right? And that affects air quality in general. And finally, there's also the concept of contrails. So contrails, if you're familiar with aviation, is basically the ice particles that form as a plane actually goes to the sky at high altitude and emits water that freezes almost instantaneously. In some cases, those contrails last for a long time, and they reflect the heat that is coming up from the Earth and contribute to global warming. So this is a relatively new insight, right? 15 years ago, people were not particularly worried about contrails, but today, people actually take this into account. In fact, if you go to flights.google.com, right, what I typically use to kind of figure out where I'm going to go when you look at the global warming potential of your flight, you can actually see the impact of contrails as predicted by Google. So that is, one of the reasons that this whole emissions reduction thing, and this is zero-emission aviation, is a very complex matter. Okay? Secondly, when you think of overall life cycle analysis and you're thinking about emissions reduction, you typically think of three things, right? How much emissions do I have during the making of the product? How much do I have during the use of the product? And then how many emissions do I actually generate when the product gets recycled at the end of its life? In the case of aviation, over 90% of the emissions are during the actual operation, right? Because the thing is burning jet fuel, and so it emits quite a bit of CO2, NOx, particulate matter, and ice as contrails during its operation. So you can't really fix it during manufacture. You can't fix it at the end. You have to fix it while it's flying or taxiing. So that makes it harder. The other thing that we have to think about is, as we think about carbonization or decarbonization challenges, is that safety needs to go first, always, every time, right? We want every flight and every mission to end successfully. We need to be conscious about energy density, right? As we're replacing jet fuel with something else, it cannot be something that weighs 10 times more because that plane needs to go up into the sky, right? And then finally, it needs to be a global solution. Because if I just solve the problem right here in Poland, right, and my flight takes off from Chopin Airport and it lands in Chicago, if we haven't solved the problem in Chicago, the plane can't come back. So the plane needs to have a global standard solution that it can rely on wherever it goes. So it needs to be a global solution at the same time. And so I'm going to make the point here in the next 10 to 15 minutes or so that the answer to replace jet fuel to get to zero-emission aviation is not a single answer. It's going to be a series of solutions that will all have to be implemented at once. So let's start with the first layer of solutions that we can easily implement. So as we like to say, the cleanest fuel is the fuel you never burn, right? So if you can somehow take every bit of efficiency into account as you're taking that flight, then you actually have immediate emissions reduction, right? Because you never burned the fuel in the first place. So smarter flight operations is something we introduced a couple of years ago, and it has a number of concepts to it. First of all, a plane actually burns quite a bit of energy when it gets from the gate to the runway. So you can optimize the taxi out. So we call this reduced energy taxi out, or RETO. You can do the same at the end of the flight, right? By the end of the runway back to the gates. And then you can optimize ascent or climb and then the descent. So if you take all of that into account and you do this through cloud computing and making sure the data is available to air traffic control and the pilot, you can actually save significant energy. Now, the trick here is to gamify this a little bit. So maybe just by a show of hands, how many people here do have a pilot's license? I'm seeing not that many, so I can be blunt. Oh, I see one there, okay. So pilots are very, very competitive, right? Is that right? Yeah. Typical alphas, right? So they will compete on anything. So if you show them data as to how much fuel you consumed in a certain flight by reducing, the amount of energy that you did during climb and descent, and you make that available, you show it how others did versus this particular pilot, they will try to win over the others. So that gamification is part of the element that we bring forward into the cockpit to show, hey, this is what you could do. And so an example of that was actually in British Airways, on the third bullet there, that perfect flight example. There was a British Airways pilot who actually achieved what we predicted as 100% flight efficiency. And he actually reduced his fuel consumption on a relatively short flight by about 370 kilograms of jet fuel, which is quite significant. It was 16% of the total consumption. Now, the other interesting thing about this is that it's very easily scalable, right? It's a software solution. The only thing you have to be conscious about is it needs to get to the cockpit in real time, so you need a SATCOM access, and you need some cloud computing to make that happen. So that's layer number one, relatively straightforward to implement. Layer number two is sustainable aviation fuel. Now, if I had done a poll at the start of this and I had said, hey, how are you going to do as this zero-emission aviation thing? Probably most of you would have said, oh, we're going to use SAF, or sustainable aviation fuel, to make that happen, right? And that is, of course, a really good solution. The first reason for the success of SAF is its drop-in compatibility, right? So SAF is chemically, essentially, almost identical to jet fuel today. And so it means that you don't have to modify the engine, you don't have to modify the storage at the airport, you don't have to modify the pumps, or maybe exchange some O-rings, but that'll be it. So the drop-in compatibility of SAF makes it very viable as a solution for the airlines. Now, when we talk about SAF, SAF is not just one thing. There are actually many, many variants on the theme. There's four big classes of SAF. The first one is the one that is currently commercial. It's called HEFA, or hydrogenated ester and fatty acids, right? So it's the used cooking oil from McDonald's that is hydrogenated and then used as basically as jet fuel. You can also use this by like linseed oil or rapeseed oil. Non-edible oils that are hydrogenated can just be used as SAF. So that's the first type. The second type that actually is now being commercialized is through the chain reaction of ethanol. Now, ethanol is an interesting story behind this, because ethanol is actually used, particularly in North America, as a blending agent into gasoline, right? And gasoline consumption, as you may know, is forecasted to go through a maximum in the next 5 years, right? Because of better fuel economy, because of electrical vehicles, etc. So the production of ethanol is expected to have a surplus. So we call this ethanol long. And so people have been looking at what are other ways that I could use that ethanol once it's being produced anyway. So we said, oh, we could polymerize it, we could chain react it into a longer fuel that looks just like jet fuel. So that's class number two. Class number three of SAF is the one that you may also have heard about, because it's basically turning household waste into fuel. This is with a big hammer technology. You basically heat it up to very, very high temperatures, and then you react it with a small amount of oxygen, you make a thing called synthesis gas, which is CO and hydrogen. You react them together, and they make jet fuel in a process called Fischer-Tropsch synthesis. So that's number 3. The fourth one, final one, is the one that is very actively researched at universities right now. It's the one where you take CO2 directly from the atmosphere, so direct air capture or DAC, right? And you react it with hydrogen that is made through splitting of water with renewable energy. And that actually creates that synthesis gas again, which you can then turn into jet fuel. So even though we call it all SAF, there's 4 different ones. They all have different timelines to get into the market. The HEFA one that I talked about first, based on non-edible oils, is the one that's currently being used. What you should know about SAF is that it's significantly more expensive to make than jet fuel. So an airline that is committed to using SAF will actually see a significant impact on their operational expense and therefore on their margins, right? So that is not negligible. The other thing to know about SAF is that its current availability is very limited. The current production of SAF is about just under 1% of the total jet fuel consumed in the world. Keep that in mind because we're going to come back to that at the end of the talk. So as you think about the other challenges that SAF has, it's limited by feedstock, right? There's only so many McDonald's in the world, so you don't have that much fry oil to begin with, right? The production capacity is an issue, as I said, the 1% of SAF that's available, the cost, and then there's other uses for biomass, right? So that SAF is made from, say, palm oil. That palm oil could be used for something else as well. So that's the SAF story. And then the third layer, and there's really 2 layers here that are interwoven because I think they're very tightly coupled, is the use of electrification and hydrogen. So that's the layer that's the furthest out. It was interesting because electrification really gained a lot of attendance when we started looking at urban air mobility, right? The air taxis, right? Because these startup companies said, oh, we're going to do this by batteries, so we don't have to worry about burning fuel and all of that. It's much cleaner. But they were forecasting very high energy densities or power densities in batteries. Okay? So they were forecasting somewhere between 250 to 500 watt-hours per kilogram on the energy content of a battery. Okay? In real life, probably most of you know, that number is 100 to 150 watt-hours per kilogram, and there's some early-stage technology that gets close to 200. But that significantly impacts the range that you can achieve on a battery, right? And remember, this is aviation. It's not like in a car that you can just put a couple more batteries in because you have to carry that thing up in the air, right? So power density or energy density is very, very important when it comes to that. So batteries are, not as successful as we thought they were going to be maybe 5 or 10 years ago. They've kind of slowed down their introduction into aircraft. And what we're actually seeing is that people are building now what I would call the Prius of the sky. So they're actually putting in a turbo machinery engine, a jet engine like you can see at our booth, and they're combining it with a battery and a generator, just like a Prius design, so that they can get the range that they want. So that's hybridization, and that's where that field has gone. The other side of this coin is the hydrogen coin, right, or the hydrogen side. So you said, hey, batteries aren't good enough, but fuel cells is the answer, right? Fuel cells are significantly more effective or efficient than, say, a gas turbine engine, so that's a good thing. But when you think about what a fuel cell needs to be effective, fuel cells are very finicky, right? So they react hydrogen on one side with air on the other side, but you need to make sure that the hydrogen is at the right temperature, the right pressure, the right humidity, and the same for the air. So when you look at the overall upside of a fuel cell system in an airplane, it's only a very small piece of the puzzle. All of the other balance of plant that you need, compression, humidification, dryers, heat exchange, it actually takes up a lot of space and a lot of weight. So combining that with the low energy density of hydrogen, right? Hydrogen, even in liquid form, is only a quarter of the energy density of jet fuel. It also very significantly limits the range. And so again, just like in the case of the batteries, with hydrogen, we want to hybridize the solution, and there's now a couple of people that are considering putting jet fuel and hydrogen tanks on the same plane and basically switching between them as the need arises for range. So that's where we're going with this. So then I think we need to talk a little bit about the supply chain, because what you heard in the last couple of slides is, there's really 3 layers of technology. We're, pretty far along on the path there. Everything is above TRL6 quite readily, so we're getting close. The problem is the sheer size of the investment that is needed to make this happen. Okay? And so there was a McKinsey study, you see the reference at the bottom of the slide there, that was done in 2022, so it's 4 or 5 years old, still very relevant actually, that said in order for us to get to zero emission aviation by 2050, the supply chain needs to invest $175 billion a year, every single year between now and 2050 to make this happen, right? So 175 billion a year. The GDP of Poland is 1 trillion a year, okay? So it's a huge amount of money, right? Some of that, about 10%, goes into modification of aircrafts. It's actually very modest, right? 17 billion a year. About 35% goes into the production of SAF. Remember, I told you SAF right now is 0.8% of the total, right? We need to get to 50% to make the zero emission aviation goal. So you need to build roughly 50 times more plants as there are out there today. So that's where all that money is going. And then the final one, the 55% left, is green hydrogen, right? And green power, because you can't really use coal-based, power to make this happen. You're just fooling yourself, right? So a total of $175 billion a year of investment for the next, 35 years to make 25 years to make all of this happen. So in conclusion, first of all, no silver bullet. We'll need all of these solutions to happen at the same time, right? So better flight efficiency, the SAF solutions, all 4 of them, if we can. And then finally, also the electrification of aircraft and the use of hydrogen. All of this needs to happen in a coordinated way in a global scale, right, such that all the solutions are available wherever the plane needs to go to. And so that's kind of a big challenge. But with a big challenge comes a big opportunity, right? So that's where we think that the complex transition of aviation actually represents magnificent innovation potential for all of us in the STEM community to really make an impact, right? So very short version here of the story. If you want to learn more, come see us at our booth. We're right outside here. There's actually two booths by Honeywell and Honeywell Aerospace. Or you could hit me up with a couple of questions here in the next couple of minutes. So with that, Monica, I'll give it back to you.
Thank you very much, Kurt, for a very interesting presentation. Now we have a few minutes. Are there any questions from the audience? So if you could put the microphone.
Okay, I think it works now. So I have 2 questions. First one considers the fact that you were saying at the beginning that the chemtrails, they were not considered to be of any danger to us even 15 years ago, but now we see that it also contributes to the global warming. And I'm wondering, is there any way to address this issue? Mm-hmm. What are we doing about this?
Yeah, so this is a relatively recent insight, right? So the problem, of course, was always there. I think we just didn't realize, right, in atmospheric science that was such a significant contributor. So one of the technologies, thank you, this is a perfect plug-in actually for me to talk about more Honeywell technology, right? So one of the things Some of the technologies that we're developing is actually a scanner. It's based on infrared laser that actually looks ahead of the plane and looks at the atmospheric conditions. It looks at the shear of wind, the temperature, the pressure, and the humidity level, and it actually calculates the likelihood of contrail formation. And then basically we send a signal to the pilot and say, hey, if you adjust your altitude by, say, 2,000 feet, right, you can actually get to a zone where there's lower contrail formation. Now, the question then becomes, by all of this going up and down, you're wasting fuel or you're burning fuel, right? So it becomes a pretty complex optimization, actually, as to, am I going to avoid contrails, but now I'm burning more fuel because I'm going up by 2,000 feet. So that's the state of the art. So we're measuring the atmospheric conditions in front of the plane, and then we'll bring that back onto the plane and then do edge computing, actually, to figure out should the pilot go up or down, or should he just stay at the same level.
Okay, that's a super interesting insight. Thank you for that. And the other one was, I was recently reading an article that I feel like it was a little bit more optimistic about the electrification of flights than you are. Mm-hmm. But I think it's because they were considering that the taxis are going to increase their range, and maybe flights across Europe are going to be easily electrificable in the nearest future. But I was wondering, what about cargo? Do we have any solutions? Are we trying to target this at this point? Because this always has a very high range of the flight, and also much higher weights. So I'm wondering about this one.
Right. So cargo is definitely, and when you look at the advanced air mobility space, like the air taxis, right, there's a cargo version of this. In fact, some of the early adopters of urban air mobility or advanced air mobility are companies like FedEx or UPS, right, the big freight carrying people, right? So they are the early adopters, and we actually are seeing interest from those companies to drive or power these devices with batteries. The range problem is still there, though. So the 250 watt-hours per kilogram number that I gave you has actually not been reached, successfully, and has led to the demise of a number of these advanced air mobility companies. They have gone bankrupt because they were betting on the fact that this was going to happen. Now, the other side of the coin is there are some companies, and you may be familiar with a company called Electra. There's a company, it's based in the United States, that is actually building ultra-short-range aircraft that are going to be wholly battery-powered. So if you're talking about a 50-mile range or maybe a 100-mile range, the solution is feasible for planes that are 19-seaters or less. So they're relatively small, like business jet size aircraft, not the Embraer or definitely not the Boeing ones. The other advantage that those planes will have is that they have ultra-short takeoff. So they can actually go up very, very steeply, which really enables their use in tightly built-up areas. So that's where that field is going. That's exciting. But if you look at where bigger planes are going to go, like a business jet, like a Learjet and things like that, we are fully expecting that is going to be a turbo generator with a battery, just like the Prius designed for a car.
Amazing, thank you.
Thank you.
Great speech.